Section 1 Introduction. We're here to discuss the exciting progress and impressive accomplishments of large-scale pre-trained language models, LLMs, in the field of natural language processing, NLP. These models have significantly improved various NLP applications, such as machine translation, summarization, and code generation. However, it's important to remember that the quality of the outputs these models generate can vary quite a bit. While individual outputs from the models often yield high-quality results, multiple outputs can sometimes produce results of much higher quality than the average output of the model. There are several ways to tackle this issue. One method is to enhance the models themselves. This can be done by adding higher quality outputs to the training dataset, as recent studies have suggested. Another strategy is to keep the model as it is but use a process called re-ranking to prioritize and select the best outputs based on certain criteria. However, most re-ranking techniques involve complex or computationally heavy methods to calculate the selection criterion, which can include training an additional model as a re-ranker or evaluating the probability of the query given the generated answer, the latter of which doubles the inference cost. In the case of code generation models, it can also involve running the generated code on unit tests, which can get quite complex and may not be feasible for a lot of use cases, especially as you move beyond the contest coding setting. Recently, for problems that have a fixed answer, a simple approach called self-consistency was suggested for selecting the best answer from multiple outputs. In this approach, the authors sample multiple outputs from the LLM, extract the predicted answer from each output and select the answer with the most votes. This method has shown substantial improvements over existing baselines, including the widely used approach of ranking outputs based on the log probability. However, the self-consistency approach is not applicable to prompts that are open-ended and do not have fixed answers. This limitation becomes particularly relevant in scenarios such as code generation, where multiple implementations of the same function may be valid, or in open-ended text generation, where multiple phrasings can convey the same meaning. The self-consistency method relies on the presence of a clear majority or consensus among the generated answers, which may not exist in these open-ended situations. Therefore, alternative strategies need to be explored to address the challenges posed by such prompt types. We can look at self-consistency from a different angle by considering a similarity function that compares different outputs and re-ranks them based on their average similarity to other outputs. In the case of self-consistency, the similarity function is binary, indicating whether the answers of two outputs are identical. However, this binary similarity function is limited to prompts that have fixed answers. In this work, we develop a framework that formally defines the concept of an optimal output. We show that this perspective on self-consistency allows us to identify the optimal output within a given set. In simulated scenarios, we provide evidence that our framework is capable of recovering the best or near-best output in many cases. Additionally, we develop lightweight similarity functions that are suitable for open-ended generation tasks, thereby expanding the applicability of self-consistency to such domains. Furthermore, we demonstrate that the re-ranking methods used in previous works can also be understood within the same conceptual framework. Our contributions are as follows. 1. We propose a generalized framework for self-consistency that extends its applicability beyond prompts with fixed answers. By formally defining the concept of an optimal output for open-ended outputs, we are able to show that our framework is capable of recovering the optimal output if it exists within the set of outputs. Through extensive simulations, we show that our approach consistently identifies the best or near-best output from a set of candidate outputs. 2. We introduce multiple lightweight similarity functions that require no additional parameters. These functions are evaluated across various tasks, including code generation, auto-formalization, and summarization, using 6 different models. Our evaluations reveal consistent and significant improvements over baseline methods. Notably, one of our similarity functions only relies on the raw outputs from the model, making it particularly relevant in situations where token log probabilities are not accessible, as is the case with certain proprietary models like OpenAI's Chat Models API. 3. Leveraging the pairwise similarity nature of our re-ranking scheme, we enhance model generation for code generation tasks, particularly when the evaluation metric is pass at k for k greater than 1. This enables us to improve the overall quality of generated code. 4. To gain insights into the effectiveness of our similarity function, we conduct various ablation experiments. These experiments allow us to analyze and understand the underlying mechanisms that contribute to the success of our approach. The rest of the paper is organized as follows. In section, we present our motivation. In section, we present our method and the similarity function. In section, we present and discuss our experimental results. In section, we describe the related work and we finally conclude in section. Section summary. The rapid advancement of large-scale pre-trained language models, LLMs, in natural language processing, NLP, has led to significant improvements in various NLP applications. However, the quality of generated outputs can vary, and existing approaches to address this issue involve computationally intensive methods. In this paper, the authors propose a self-consistency approach that selects the best answer from multiple generations by extracting the predicted answer and selecting the one with the highest number of votes. They also develop lightweight similarity functions suitable for open-ended generation tasks, demonstrating consistent improvements over baseline methods. Section 2: Motivation. We're trying to understand what makes a good generation. In the realm of code generation, for example, we might measure this by the number of successful unit tests, which gives us a rough idea of how correct the code is. Other factors could include how easy the code is to read or how computationally efficient it is, as determined by human evaluators. For language tasks, we could set up a similar set of criteria to judge the quality of the output, such as how fluent it is, whether it avoids creating content that wasn't there before, or how accurate its responses are to questions with set answers. To put this into formal terms, let's imagine a vector, or list, of length k, where each item represents a different category. We also have n people, each of whom has their own estimate of what this vector should look like. The only information we have access to is the fractional agreement between pairs of these estimates, which is a measure of how much they agree. Our goal is to find the person whose estimate aligns most closely with the vector we're interested in. In this setup, the items in the vector represent the different criteria we want the generation to meet, and the people represent different generations. We're assuming that we only have access to the fractional agreement, not the underlying estimates, because we might not have the resources or knowledge to evaluate all the criteria on the different generations at the time of inference. For example, in the context of code, we might not be able to run unit tests due to time or security constraints, or because we don't have the right build system or any unit tests available. For criteria like avoiding content creation, human evaluation might be needed, which isn't usually possible at the time of inference. As a result, we have to approximate the agreement using proxy similarity functions. We're making the assumption that, for each individual criterion, the most common response is assumed to be the correct one. Given this problem setup and selection criterion, we can state the following. Theorem 2.1. If we're only looking at one criterion, we'll always find the best estimate. But if we're looking at more than one, it's not guaranteed. Theorem 2.2. If there's a generation whose criterion vector perfectly matches the target vector, choosing the generation with the highest average fractional agreement with other generations will select this generation. Theorem 2.3. If we assume that the elements of the estimate vectors are independently and identically distributed from a Bernoulli distribution, then we can show that the expected value of the sum of the elements of the selected sequence is within a certain range. We've provided proofs for these theorems in the supplement. To further support our selection criterion, choosing the generation with the highest average fractional agreement with all other generations, we ran a simulation. We randomly generated vectors and estimates and evaluated how well our criterion worked. Our results suggest that for various numbers of criteria, our method successfully finds the best generation most of the time, significantly better than random selection. Furthermore, on average, the generation we find agrees almost completely with the best generation, even when we don't select the best generation. We've provided full details in the supplement. Section Summary. The motivation behind evaluating the quality of code generation or language tasks lies in establishing criteria such as correctness, readability, and computational optimality. To formalize this evaluation, we consider a vector representing categorical variables and personal estimates from multiple individuals. By measuring pairwise fractional agreement, we aim to identify the person whose estimates align the most with the target vector. However, due to resource constraints, we approximate agreement using proxy similarity functions and assume that the most frequent response for each predicate is correct. Theorems are presented to support our selection criterion, and simulation results demonstrate the effectiveness of our method in recovering the best generation. Section 3: Method. As we've mentioned before, we might not always be able to calculate predicates at the time of inference, which makes it impossible to compute the exact fractional agreement with v, or a, u, v. Because of this, we need to use a substitute similarity function. We create a generalized self-consistency score, or GSC_sim, I, for each generation I. This score is calculated by taking the average of the similarity function, sim, across all generations except the current one. The number of generations is represented by m for generations that have fixed answers. The similarity function, sim, I, j, is 1 if the answer in generation I matches exactly with the answer in generation j. This is the same as the self-consistency criterion. Two other re-ranking methods, MBR-exec and AlphaCode, use the same formula but with different similarity functions. MBR-exec runs the code generated by the model and assigns a similarity score of 1 if two programs agree on all unit tests, and 0 if they don't. They calculate this by taking the sum of the similarity of each program against all other programs and choosing the program with the highest similarity. AlphaCode, on the other hand, groups its generated programs by running them on test cases and picking a program from the largest group. This is similar to what MBR-exec does. We can also use an OpenAI ADA embedding-based similarity function, which shows promise, but it requires a separate embedding model, so we decided not to explore it further. A simple way to encode a generation is by using a binary vector that indicates whether an n-gram is present or not. We found this simple encoding to be enough for defining a robust similarity function. For open-ended generation, we define our similarity function as follows. For each generation, we create a vector, v, of size, v, where v is the set of all possible n-grams for n equals 1 to n equals k, with k being a hyperparameter. For this paper, we used k equals 1. Each element I of v indicates whether token I is present in the generation or not. We then calculate the inner product between two such vectors as the similarity. We call this the n-gram consistency score, NCS, and the k equals 1 version as the unigram consistency score, UCS. When token probabilities are available, we can use them to improve our approach. If a generation has a low token probability for the generated token, then finding a match for that token should count for less. With this in mind, we introduce two more variants. First, we modify the definition of v to take into account the number of times a token appears in a generation and the token probability of each appearance. We call this the weighted n-gram consistency score, WUCS. We can also combine the mean log probability of a sequence, a common ranking method, with WUCS by further weighting each generation by the per token probability. Finally, to rank the generations, we use the generalized self-consistency score, GSC_SIM, I, where SIM can be UCS, WUCS, or consensus UCS. Section summary. The authors propose a surrogate similarity function called the generalized self-consistency score, GSC_SIM, to measure the agreement between generations in a language model. They define different similarity functions such as the unigram consistency score, UCS, and weighted unigram consistency score, WUCS, based on the presence or absence of n-grams in the generations. They also introduce consensus WUCS, which combines WUCS with the mean log probability of a sequence, to rank the generations. Section 3.1 Extending to ranked pass at K. We're going to discuss how we can improve the evaluation of code generation problems by extending the ranked pass at K metric. This metric is commonly used to evaluate whether any of the top K programs, chosen from a larger set, can pass all the given unit tests for a problem. Usually, the top K programs are chosen based on a preset ranking. But, with our similarity-based metric, we can use a more refined approach. Let's say we have a specific problem. If the top-ranked program for this problem is correct, then we've already succeeded. We would only need to use the other programs in our top K selection if the top-ranked program fails some unit test. In this case, we could treat the top-ranked program as a hard negative and choose the next program that is less similar to the top-ranked one. To be more specific, if we've chosen programs S_K, so far, where the number of chosen programs K is less than K, we adjust the GCS function to select the K plus 1 TH program in the list. We calculate the ranked GCS based on similarity as the average difference between the similarity of the unselected and selected programs. It's important to note that when K equals 1, the GCS and ranked GCS are the same. We show in a later section that the ranked GCS based on similarity performs much better in ranking for pass at K where K is greater than 1, compared to the raw GCS. This method allows us to use the ranked programs more efficiently, improving the overall effectiveness of the code generation task. Now, let's talk about our results. We conducted experiments using the Codex and Llama model families, as well as the GPTJ model for XSUM and Mini F2F. We tested these models on various datasets for code generation tasks, specifically the Human Eval, MBPP, and MBPP sanitized datasets. For the auto-formalization of Mini F2F to Isabelle, we used a provided dataset. For text summarization, we used the XSUM dataset. Our main evaluation metric for code generation is ranked pass at 1, where we re-rank a sample set of programs and check if the top-ranked program passes all unit tests. We also evaluated using ranked pass at k for k greater than 1. For the mini F2F auto-formalization task, we measured the quality using the blue score. For XSUM, we used the Rouge 2 and Rouge L scores for evaluation. For all code generation datasets, we sampled 125 programs from the models, which served as our dataset for the different experiments. For mini F2F and XSUM, we sampled 50 programs from the model. Unless stated otherwise, we used the Codex DaVinci 002 model for all experiments. We performed bootstrap sampling 50 times with a sample size of 25 to generate the results. Our baselines were random selection, ranking by mean log probability, ranking using centroid in our confidence-weighted unigram space, and for code generation, ranking using the coder reviewer ranker method. A full description of the datasets, experiments, and the baselines is in the supplement. Section Summary. In this section, the authors discuss the extension of the evaluation metric for code generation problems to ranked pass at k. They propose a similarity-based approach where the top-ranked generation is considered correct, and only if it fails some unit test cases, the next generation with lower similarity is selected. This approach improves the efficiency and effectiveness of the code generation task. The authors also provide details about the models, datasets, and evaluation metrics used in their experiments. Section 4.1 UCS scores are higher for correct answers. We'll start by discussing the results of our sanity check, which aim to confirm whether the UCS scores were indeed higher for correct answers. We used the generations provided in the supplementary material for this evaluation. The results, which can be found in the supplementary table, show that the ratios are consistently greater than 1 for all models. The only exception is the UL2 to 20B model, but even for this model, the ratios remain very close to 1. Next, we'll discuss how the UCS, WUCS, and consensus WUCS methods have significantly improved the accuracy and mean reciprocal rank of code generation across various models and datasets. This is clearly demonstrated in the tables. In the human eval dataset, these UCS variants consistently outperform traditional methods like random and mean log probability. For example, the Codex 002 model's accuracy improved significantly from 0.435, using random, to 0.568, using consensus WUCS. Even models that don't perform as well, like Llama 13B and Llama 30B, show noticeable accuracy improvements when we use our proposed methods. We observed similar trends in the MBPPS and MBPP datasets. Across all models, UCS, WUCS, and consensus WUCS consistently improve accuracy. In particular, the consensus WUCS method consistently outperforms random and mean log probability ranking in all categories, and almost always performs better than WUCS as well. WUCS also stands out, as it surpasses the mean log probability method in every model and dataset combination. The only exception is the Llama 13B model for MBBP and MBPPS. UCS, which doesn't require token probabilities and only relies on the generations, consistently outperforms random re-ranking. Consensus WUCS and WUCS also almost always perform better than the centroid-based approach, with consensus WUCS outperforming it 13 out of 15 times. We'll discuss the mean reciprocal ranking performance in the supplement, but the trend is similar. Section Summary. The UCS scores are evaluated to determine if they are higher for correct answers, and the results show that the scores are consistently higher for all models except one. Additionally, the application of UCS, WUCS, and consensus WUCS methods leads to significant improvements in the accuracy and mean reciprocal rank of code generation across various models and datasets, consistently outperforming traditional methods such as random and mean log probability. Section 4.3 UCS shows consistent improvements for open-ended generation. In Section 4.3, we discuss how the UCS, WUCS, and consensus WUCS methods consistently improve open-ended generation. We tested these methods on the XSUM and mini F2F datasets, and the results were promising, showing that our proposed methods are versatile and effective across different tasks and models. When we evaluated the mini F2F dataset using the blue metric, we found that consensus WUCS performed better than all other methods for the Codex 002 model, except for centroid. For the Llama 13B, Llama 30B, and GPTJ models, the top performers were closely matched, with consensus WUCS, WUCS, and UCS all delivering competitive scores. We observed a similar trend with the XSUM dataset. For the Rouge 2 metric, consensus WUCS achieved the highest score for the Codex 002 in both Llama models, and tied for the best score with WUCS for the Llama 13B model. In the GPTJ model, UCS performs slightly better than the WUCS and consensus WUCS. However, all these methods outperformed random and mean low-GP re-ranking methods and almost always outperformed centroid. When we used the Rouge L metric, the UCS variants showed the best performance for all models except Codex 002. For the Llama 30B model, WUCS and consensus WUCS shared the top spot, while UCS achieved the best score for the GPTJ model. Again, these methods generally outperformed centroid, random, and mean low-GP re-ranking methods. In total, consensus WUCS was the top performer in 5 out of 12 comparisons, WUCS in 4 out of 12, UCS in 2 out of 12, and centroid in 5 out of 12, primarily due to mini F2F. In section 4.4, we compare the UCS variants with the code reviewer ranker baseline, specifically with the normalized reviewer, NR, and normalized coder reviewer, NCR, variants. These methods are considered the state-of-the-art in code re-ranking, so they represent a strong baseline. Our results show that the WUCS and consensus WUCS methods are highly competitive, often outperforming both NR and NCR, even though NR and NCR require a second forward pass, which doubles the inference cost and adds latency overhead. We discuss these results in more detail in the supplement. Section Summary. The section discusses the consistent improvements shown by UCS, WUCS, and consensus WUCS in open-ended generation tasks. The results on the XSUM and mini F2F datasets demonstrate the effectiveness of these methods, with consensus WUCS outperforming other techniques for the Codex 002 model in terms of BLEU metric. Additionally, the UCS variants are competitive with the code reviewer ranker baseline, often outperforming it despite the additional inference cost and latency overhead. Section 4.5 improvements are consistent across different generation temperatures. We've observed consistent improvements across various generation temperatures. In one of our figures, we demonstrate how the re-ranking behavior of UCS changes for MBPP as the decoding sampling temperature rises. Although accuracy can fluctuate with different temperatures, the ranking order of the various methods remains stable. The consensus WUCS method consistently outperforms others in terms of accuracy across most temperature ranges, up until the temperature reaches 1. Notably, at lower temperatures where we see the best results, both consensus WUCS and WUCS achieve the highest accuracy. UCS performs comparably to mean log probability ranking up to a temperature of 0.4, after which it starts to lag. However, it's important to note that UCS doesn't use any probability information about the generation, so a fair comparison would be with random ranking, which UCS consistently outperforms across almost the entire temperature range. We also found that changing the maximum n-gram length doesn't affect the results. As we mentioned earlier, UCS only considers unigrams. In this section, we look at the n-gram consistency score, a more generalized version. To adjust for the fact that a sentence will have fewer n-grams as n increases, we multiply the probability of the kth appearance of the jth n-gram in the ith generation by the ratio of the length of the ith generation to the difference between the length of the ith generation and the length of the jth n-gram minus 1. In another figure, we illustrate how the ranking changes as n increases. While there's a slight improvement when n increases from 1 to 4, the improvement plateaus after that. Interestingly, 4 grams are also typically used when calculating the BLEU score, so it's intriguing that the same value is optimal in the significantly different context of code generation, where each word is a token rather than an English word. Lastly, we found that increasing the number of samples maintains the re-ranking strength. In another figure, we demonstrate how the performance of MBPP and XSUM changes as the number of samples increases. All versions of UCS are able to maintain accuracy, although consensus WUCS initially sees a drop for XSUM but maintains its performance afterwards, even as the number of samples increases from 5 to 100. In contrast, the accuracy of mean log probability ranking drastically declines, quickly falling below even random selection. This is likely because mean log probability ranking tends to choose degenerate sequences, which the UCS variants seem to be able to avoid. Section Summary. The accuracy of the UCS re-ranking method remains consistent across different generation temperatures, with consensus WUCS performing the best for most temperature regimes. Varying the maximum n-gram length does not significantly affect the results, as the improvement in ranking flattens after n equals 4. Increasing the number of samples maintains the re-ranking strength of UCS variants, while mean log probability ranking quickly declines in accuracy. Section 4.8 GCS-ranked comparison. In section 4.8, we compare the performance of two models, GCS and GCS-ranked. The figure illustrates how the performance of these models changes as the value of K in pass at K increases. The GCS model's performance drops rapidly, while the GCS-ranked model maintains a high level of performance even when K is large, across all code generation datasets. In section 5, we discuss related work. Section 5.1 focuses on advanced decoding methods aimed at enhancing the quality of model generation. Some methods adjust the log probabilities of tokens based on their similarity to previously selected words. However, this approach requires joint generation with coordination, which can lead to significant infrastructure and latency overhead, especially if the model is distributed across multiple GPUs or machines, a common scenario for large language models. LLMs. Other methods use an auxiliary LLM model to compare token probabilities against the primary LLM for decoding. Some methods penalize the generation of already generated tokens. A common limitation of these methods is that they require access to the LLM's decoding procedure. You can't simply use the generations from an LLM API. Our approach is somewhat similar to one where a consensus hypothesis is computed by aligning multiple sentence lattices. Section 5.2 discusses the use of an auxiliary reranker. Some methods use a perceptron-based reranker to reorder model-generated translations. The SUMA reranker uses a mixture of experts training to train their reranker to optimize for multiple automated evaluation metrics, like Rouge or Blue score, simultaneously. The pair reranker uses automated evaluation metrics to rank model generations, then selects the top few best and worst, and trains a model to classify the better summary between a pair of summaries. However, all these reranking methods require training an auxiliary model. Section 5.3 talks about reranking proposals specifically for code generation. A unique feature of code, compared to text, is that it can be executed. Therefore, several methods have attempted to use this property for reranking. MBR-exec and AlphaCode both run the generated codes on unit tests. They rank the different codes based on how many other codes produce the same results on the given unit tests. Codeit uses LLMs to generate both code and candidate unit tests. They then find sets of generated codes such that the product of the size of the set and the size of the unit test set the codes agree on is maximized. More recently, the Coder Reviewer Ranker applies the well-known maximum mutual information objective to code-generating LLMs by using the strong few-shot and zero prompting capabilities of LLMs to obtain the query likelihood. Section Summary. In this section, the authors compare the performance of GCS and GCS-ranked models for code generation datasets. They find that while the performance of GCS declines quickly, GCS-ranked maintains good performance even at larger values of K. Additionally, the authors discuss related work on advanced decoding methods and auxiliary rerankers for code generation, highlighting the unique characteristics of code and the use of execution and unit tests in reranking proposals.